These are the Pythagorean Theorem Part 2 notes. Make sure you've already watched the Part 1 notes before you start in on this. As we continue with our work on Pythagorean Theorem, we want to give you some tips for how to use the Pythagorean Theorem in application problems. A lot of times people say, how will I ever use this? Pythagorean Theorem is very useful in lots of different scenarios. So when you come across a problem where you're going to need to use it, we want to give you some recommendations. First of all, make sure that you sketch a picture, some kind of diagram. If they haven't already given you one, it's going to be really helpful for you to visualize the information. And in fact, make sure that in your sketch, you label all of the different pieces with any measurements they've given you. You should also emphasize the right angle, the right triangle in your picture. There are lots of ways that you can emphasize that right triangle. So either using a different color or just with your pencil darken in the edges so that you can focus on the right triangle part of the whole picture. It also helps to draw in the right angle in the diagram, as well as labeling your legs A and B and labeling your hypotenuse C so that you know which parts of the formula you already have. Lastly, stop to think about what is the question asking you to find. Because while you may need the Pythagorean theorem in order to find a missing side length of a triangle, that may not actually be the answer to the question. That may be part of a process, and then you take that answer and use it to do further problem solving to get to the answer. All right, so let's take a look at an example. A rectangle is 15 centimeters tall and 8 centimeters wide. How long is its diagonal? So I'm going to start by drawing a picture. I don't need to worry about my picture being completely accurate. I don't need to get a ruler and measure 15 centimeters tall and 8 centimeters wide, but I do need to make sure that I label. If you'd like, you can also label the other two sides, but that may be a little bit of overkill. How long is its diagonal? So a diagonal, right, is a line connecting two vertices that aren't already connected by a side length. Here's this diagonal. It would be the same diagonal if I went the other direction, so if you already drew in the diagonal that way, that's fine. But here, maybe I start to see my right triangle, and we know it's a right triangle because we know that rectangles have right angles in the corner. So hopefully you see your right triangle in this diagram. And I am emphasizing it by drawing in a different color, and I'm drawing in my right angle, and I am labeling the sides that I already know, and I am labeling the side that I don't know. So now I can see, oh, that diagonal that I want to know, that is the C, that is the hypotenuse. So it makes it easier for me to work because I already know what I need to fill in, what I need to solve for. 8 squared is 64, 15 squared is 225. When I add those up, I get 289. So the square root of that, 289, is actually, 289 is a perfect square. It works out to be 17. Let me move that up where you can see that. And I need to remember my units. Pythagorean theorem is often used to find measurements. Don't forget your units in those answers. So my answer is 17 centimeters. All right, for this picture, for this problem, we have a pole that ended up broken here in sort of the middle. I don't want to say the exact middle. Somewhere in the midst of the pole, it was broken in half. And this is the information we know in here in the picture. How tall was the pole originally? I want you to pause the video, and I want you to try to solve this on your own. Okay, so now you should be coming back after attempting this problem on your own, and let's see what we've got. So I already have a picture, yay, I don't need to draw one, but I do want to emphasize my right triangle. Well, there's not a right angle in here. The right angle is implied. Hopefully my pole was not sticking out of the ground at some weird angle. Hopefully it was standing up nice and straight, making a right angle to the ground. So I'm emphasizing, right, my right triangle in there with the right angle. Let's label what I already have and what I don't know. All right, so I already know that A is 3 feet, B is 4 feet. I am missing the hypotenuse of C. Remember that third part. What is the question asking me for? Is the question asking me for how much of the pole was broken off? No, the question is asking me how tall was the pole originally? How am I going to find that? I'm going to have to add leg B to hypotenuse C here in order to find my answer. So it's important to kind of take note about that before I start doing my Pythagorean theorem. I get so excited that I found the answer to my Pythagorean theorem that I forget that's not actually the answer to the question. So let's use my Pythagorean theorem to find the information I need in order to be able to add those two side lengths up. A is 3 and B is 4. When I square those numbers, I get 9 and 16. Added together give me 25. So I know that C is the square root of 25, which is 5. And my units need to match, so 5 feet. However, I remember that in order to answer the question that I've been asked, I need to add B and C together. So this part of the pole is 4 feet, plus this part of the pole that was 5 feet, tells me that the pole was originally 9 feet tall. Another way to apply the Pythagorean theorem is to test a triangle that you already know all 3 side lengths for and find out, is it a right triangle? You don't know the angle measures, but you do know all 3 sides. What you can do is fill in A, B, and C, fill in all 3 side lengths into those 3 letters, and do the math. Check to see if the formula works out correctly and gives you a correct equation where both sides are equal. If so, then those 3 side lengths can make a right triangle. The thing you have to remember, though, is when testing the numbers, make sure that whatever your largest side length is, you fill in for C into the Pythagorean theorem. Because otherwise, your math will all be wrong, and it doesn't matter if it's a right triangle or not. If you're not filling in the largest number as C, it's going to come out wrong no matter what, even if it is a right triangle. So let's look at a couple of examples. If I have a triangle with side lengths of 7, 9, and 6 units, I want to do these 3 numbers in my formula, in my Pythagorean theorem, but I have to remember to put the largest one in as C. What's the largest one? 9. 9 has to fill in for C. My 2 shorter sides are my legs, and it doesn't matter which one is which. Now, I shouldn't really put an equal sign here. I don't actually know if it's equals. Let's do the math and find out. 6 squared is 36. 7 squared is 49. 36 plus 49 is 85. 9 squared is 81. Those 2 sides are not equal to each other. So no, not a right triangle. Okay, gang, due to technical difficulties, I've had to record a small part of this video. We were looking at this example and going to test if these could be the side lengths of a right triangle. It may look a little strange since we have irrational numbers as our side lengths, but we can do it. First, I have to figure out which is going to be the C value. Which of these is the largest? So let's go back to talking about how we approximate our square roots. Since 10 is really close to 9, we know the square root of 10 is going to be really close to 3, the square root of 9. 15 is close to the perfect square 16, and so the square root of 15 is going to be pretty close to 4. Those are definitely both smaller than 5, so when I fill in my Pythagorean theorem, I can fill in 5 as the C value because I know it's the largest. Now, when I'm looking at this, this may look really complicated, but actually it's really easy. Square rooting and squaring are opposites of each other, just like adding and subtracting or multiplying and dividing. And since they're opposite operations, they undo each other. If I add a number and then subtract that same number away, I'm back to where I started. So when I take the square root and then immediately square it right after, those are going to undo each other, and I'm going to be back to the 10 I started from. Same here. When I take 15, find the square root of it, and then square it, those will undo each other, and I will just have 15. 5 squared is 25. So I check. 10 plus 15, does that equal 25? It sure does. So yes, it's a right triangle. Now it's your turn. Pause the video. Let's see how we did. In this first triangle, it's a little bit obvious. 89 is our largest number and has to be our c squared. So we need to do some math to figure out what these numbers squared are. Yes, that means you have to do some longhand multiplication, but it is not that hard. See, look, your teacher is doing it with you. $80 squared is a lot easier. Because what happens? I can write down the zeros at the end and focus on the 8 times 8, which is 6,400 when I'm all done. And then 89 squared. So I need to find out, does 39 squared plus 80 squared equal 89 squared? Does that work out correctly? Yes, it does. So yes, it's a right triangle. Second example. We have another one of those irrational side lengths. Between these two, 7 is bigger than 6, so I need to figure out, is the square root of 12 bigger than 7 or smaller than 7, so that I know if it should be the c value. You cannot trust the picture. Never ever trust the picture. You have to assume that whoever draw it, has about the level of a third grader's drawing skills. You cannot trust that they've done it well. So, we have to approximate the square root of 12. Well, 12 is between the perfect squares 9 and 16. So the square root of 12 is going to be between the square root of 9 and 16. It's going to be between 3 and 4. And that's definitely smaller than 7. So when I fill this in, I'm going to need to fill in 7 as my potential c value. The square root of 12 squared, remember, that's super easy because square rooting and square cancel each other out. 12 plus 36, oh, that's 48. Oh, we got close, but close does not count. No, it is not a right triangle. Last piece of advice here in this video. You may have seen in our work over the last couple of days with Pythagorean Theorem that some groups of numbers end up being used more often than others in examples. These numbers are called Pythagorean triples. A group like 3, 4, 5. You're going to see those numbers and multiples of those numbers in examples a lot because they make the Pythagorean theorem work out to be true, and they're nice whole numbers that are easy to work with. But they're not the only ones. 5, 12, 13, 7, 24, 25. I've written a few more down over here, and there are infinitely many more. These are called primitive Pythagorean triples because I can take them, I can scale them up by taking every number and multiplying them all by the same scale factor, and that will give me another Pythagorean triple. So 6, 8, 10 could be the side lengths of a right triangle. And just like memorizing multiplication tables, if you can memorize your Pythagorean triples, at least a few of them, and learn to recognize them, that saves you the work of having to use the Pythagorean theorem every time. If you recognize a problem, and what they've given you is that this side is 12 and this side is 13, and we want to find this side, you don't actually have to do the work. You can just say, it's a Pythagorean triple. The answer is 5. But we please ask that you write down on your paper, Pythagorean triple, before you just give us an answer. That's it for today. Hopefully this is going to help you when you come into class and get to work on some application problems.